All right. First, I apologize for my voice. I was sick like 3 weeks ago, and it still wrecked my throat. So bear with me. Good evening. Welcome to tonight's segment of the Faculty Lecture Series. I am Jessica Lardy, professor and director, and I coordinate the series. Thanks for attending tonight's lecture. Keep an eye out for upcoming lectures. There's a rack card over there and a schedule right outside the doors. Next week on Wednesday, we'll have a lecture featuring Professor Yusri Zaro of Business. And then Thursday, we'll have a lecture by Dr. Choyan Lahiri of Geosciences. This evening's event is presented by Dr. Kazi Zawad Arefin of Computer Science in the School of Science, Technology, Engineering, and Mathematics. Dr. Arefin is an assistant professor of computer science and has expertise in data science, mHealth, and artificial intelligence. His research focuses on developing non-invasive health monitoring systems and AI-powered interventions for resource-constrained medical conditions. He received his PhD in computer science from Marquette University, where he worked on projects including contactless oxygen saturation detection, I might need that, EMR systems for autism treatment, and remote vital sign monitoring using smartphone cameras and machine learning. His work has been presented at IEEE conferences and published in journals such as Smart Health. Dr. Arefin brings industry experience as a research data scientist at Direct Supply and as a data analysis at Northwestern Mutual, where he applied machine learning and data visualization to drive decision-making and operational efficiency. Committed to inclusive education and interdisciplinary research, Dr. Arefin actively mentors students and collaborates on health tech projects. So tonight's lecture is titled AI in Healthcare, Are We There Yet? And in his words, AI is revolutionizing every domain nowadays. Technology in healthcare is an area which has seen significant advancement in the recent years with remote health monitoring and point-of-care solutions to assist doctors in providing better care. Predictive diagnosis and health forecasting for multimodal data of patients captured from electronic medical records and health monitoring is said to revolutionize affordable healthcare possibilities. But as with other implementations of AI, this field of ideas is facing a lot of skepticism. In this lecture, he will share with you how AI is being implemented in healthcare and future implications. So help me in welcoming Dr. Arefin.
So first of all, thank you, Jess, for the introduction. I appreciate everybody in the audience who showed support, came in for today's talk. And without further ado, let's start with today's talk, which is AI in healthcare. I have been doing my research for technology in healthcare for the past 5 years during my PhD. I was working in fintech before that. Basically, my idea was if I'm going to use computer science, it should be somewhere where the impact was most, at least to me. And I found that healthcare was an area that usually didn't receive much of the focus when we talk about revolutionary technologies, both in computer science and probably some part from mechanical engineering as well. So right now, with the evolution of AI, it's being used in healthcare as well, like very extensively, often not so much for the eyes that we can like experience it. But today I'm going to share some of the areas that what I have worked with, where I have experienced AI is making greater impact for healthcare. And the most important part, where like whenever I was doing my research, I faced several kind of skepticism about how this kind of technology is going to abrupt the way we are thinking about healthcare right now, because a part of healthcare is mostly it's related, it's mostly very closely related to some of human intelligence as well. So how AI is going to deal with that and where are we lacking behind, we're going to talk about that as well. So before starting anything, I want to set some expectations about artificial intelligence, where we are at right now, and how is it being used not only in healthcare but in different aspects of like modern implementations that we see all around. So the first overarching question that we might have is, what is AI? Now, with like in the beginning, or when the AI was just being brought up on or being shed light, it was like the brainchild of John McCarthy at the Dartmouth College. He basically organized a kind of a seminar for people who were like-minded, who were really interested in some implementations of AI. AI was just a thought beforehand, like it was just a thought from Alan Turing, but it was not something that people were thinking about how we can actually implement it in real life scenarios or computer science applications. So John McCarthy first made that happen. During that seminar, their idea about AI was they wanted to build something that kind of represented seminal intelligence, not something that we are seeing right now. Their idea of AI was some kind of intelligent tool that could solve any problem that is thrown at its hand. But right now, where AI has like been pinned upon is kind of anything that can at least mimic human intelligence is being called at least part of artificial intelligence. But the initial idea about artificial intelligence was not that. It was kind of an idea that an overarching solution that could solve any problem that the humanity might have. With that, I want to talk about some of the components of AI that are being used in today's implementations. The most comprehensive idea that AI is bringing about right now or in today's implementations comes from machine learning. So what machine learning does is it kind of sets a way for the machine to actually learn from predefined data, from data that is probably unskewed and generated randomly. But the idea of machine learning is to at least get the machine to know about what to expect and to predict in future by seeing the data that has been provided to it. Next came in, or next idea that's like being heavily used as well, is neural networks. Neural networks are kind of a combination of the ideas stemming from machine learning and also mimicking the way a brain processes information, with neurons being the most crucial or component parts and the network behind them kind of sufficing the knowledge representation, which is being seen in most of the implementations that we have right now. Next thing that's like a core component of AI and is being implemented in many solutions is natural language processing. And as the name stands, it basically works with textual data and kind of tries to actually find the predominant sequences that we might find in a textual representation of any kind of data that we can imagine. Last but not the least, this has just started, but robotics is another place where machine learning is making a huge impact. Probably like we have seen robotics with kind of implementations that were not possible before, where robots couldn't understand where their steps, or robot couldn't understand the tasks that they were set upon. They were only predominantly coded with a set of tasks, but machine learning right now is enabling them to do the things that they haven't learned before or they weren't taught before, kind of predicting or simulating the way with the data that's being provided to them. Next comes in kind of what, like with the idea that how artificial intelligence actually performs or what's the core concepts behind it. Next comes the idea about how artificial intelligence can be used in healthcare. So we start with some like AI being introduced to healthcare started with some like pretty simple and like predefined tasks like drug development, where you at least have the idea about what kind of like combinations chemical combinations do you want, and when you are developing a drug you just like kind of shift and try out different combinations until you find something that's really working. Then virtual nursing assistant was another thing that like came way before, even like when AI was being used predominantly. Fraud detection was another part where like it's not only in healthcare, it's being used mostly all over the place, but AI was a pretty good solvent for that as well. But some of the areas that is being like discovered right now, that is being heavily used right now, are medical diagnosis, cancer research, and personalized healthcare plans. I have worked on like building some ideas about how personalized healthcare plans can be affected with the AI models that you use. Also, cancer research is being heavily like affected by it, because what you often have in cancer research is you have some set about symptoms that you need to figure out. You have idea about who is showing what kind of symptom. You just can't predict in the future like who is going to be affected by what. AI is pretty good in this. AI is pretty good in forecasting. So if you have like a certain amount of data, available data on patient care research, you can actually predict the outcome of each of the patients that you are dealing with. And one other part that's being like other two parts that are also showing promise with AI in healthcare is health monitoring and wearables. So as AI works with data, and healthcare data was only with electronic health records beforehand, but with the advent of wearables and health monitoring devices, these are being pretty common for the people who are like working or even like sharing data when they are at home. So those data are really important to train a model that could like define some probabilities that what could lead to a medical diagnosis beforehand. And also gene editing is something that's being heavily affected by AI. For the next part, we will talk about what makes it work. So the idea is the AI models that we use right now is heavily dependent on data, and without data it's really difficult to actually think about predicting something accurately. And the good news is for healthcare data, whenever we are talking about healthcare data inside electronic health record or something that some organization that's dealing with healthcare data, they need to at least maintain some standards whenever they are storing the data, whenever they are using the data, even whenever they are sharing the data. that's called HIPAA compliance, and that's kind of a necessity whenever you are dealing with medical care data, and also you need some kind of like some kind of audit as well inside your organization when you actually deal with healthcare data. But the thing is, there is a caveat as well inside that. The caveat is, uh, according to the Public Health Act, you can't really pinpoint each of the data point to each individual that had that symptom, and that's something that creates a like hurdle for anyone who is defining a AI model based on the data that we have, because the idea is if you can't really define an individual with a symptom, then you really need to predict something over the board, which kind of doesn't really pinpoint diagnosis or symptom. But the data that flows through the healthcare technology comes from medical claims, from insurance claims, from predominantly from electronic healthcare records, because those data are considered kind of state of the art, and their accuracy and validity is kind of accepted. And one other thing where data is being pulled in for AI models that are being used in healthcare is government health plan and health plan claims. So these kind of combine the data sets and kind of make what AI models are right now with data. Next thing that AI models really need to do, or whenever they are performing their tasks, they need to basically extract features from the data that is available to them. These features are basically what fed into the models, and you can think about these features as just numbers. Why I included this? Because my idea was, if the idea that the models that the AI models that are predicting health diagnoses, they work randomly or under a black box, but that's not true. They are basically working with the data points that you are sharing with them, extracting the relevant features from those data points, extracting the relevant trends from those data points, and trying to make the predictions upon them. It's not something that's black box, it's not something that's out of the blue. It's something that heavily depends on like predefined mathematics, and also like it has theoretical resemblance as well, because it's being widely used in other areas as well. So what happens is, whenever you have some kind of medical data, you start with the data acquisition. So where you gather the data, pre-process the data, clean the data, and most often medical data are like cleaned up, and they also are accurate in most cases. After that, you extract relevant features of the data depending on some kind of field specialization. Maybe a doctor, a clinician comes in and says that, okay, for these parameters or these ideas, these are relevant. And then with all the features, you actually work with the training the model and actually getting the prediction. So whenever you're thinking about a system, building an AI system that's gonna like serve people in mass, you need to think about 3 core components. That starts with limited clinical practice. What like the major concern is, even if I build something that's really close to, that's giving me good accuracy, that's like accurately predicting the diagnoses that I had imagined, but the idea stands still because people are really not finding it acceptable to actually depend on an AI based on the decision that it's making, even in cancer research or something like that, because it's a matter of life and death. So limited clinical practice is a like core component that you need to think about when you are building these kinds of system. Design and develop stage, this is the part where you kind of make it user friendly so that the user has idea about the decisions that the AI models are making. It has some like background, it has some theoretical background that suffices, okay, this should come about. And last but not the least are the evaluation and validation stage. So you can't really think about setting up a AI model without properly validating it and over time. So in the design and development stage, what we do is we're going to talk about the limited clinical practices afterwards in the slides, because that's a pretty like my core component of even if I try to build proper AI models, what happens next, that's kind of a part of that. So whenever we talk about design and development stage of AI, we find that the first thing that we need is the data that we want to actually model upon. Then we need to make some prototypes of our model, or maybe some kind of like some solution or a prototype that could at least be handed out to clinicians, which can be tried out and like kind of evaluated if what the clinician is saying and what the model is saying true. And also this happens with the collaboration between clinicians and the technologists that are working with the AI model. So the idea is, like in my experience, often when I have worked with clinicians, they have pretty good idea about what they are working on, but they are also very stringent about accepting AI in their day-to-day tasks. So most of the time, what happens for someone who is working on this field is kind of a chunk of their time goes into actually understanding the requirements, because the requirements for a clinician is not something that's straightforward. You need to talk to them. You might need to go over and see how they work, what they work on, or how they interact with people. And even the validation even at the validation stage, you need them, because it's not something that if you see a good accuracy number for your model, it means your model is good. You need the clinicians again kind of trying to see that if the views or what the model is predicting is kind of aligning with the clinician is thinking about the patient. And that's what kind of the evaluation and validation state does. It rigorously, like first the data collection process is often like dealt with different IRB or institutional revenue boards, often across universities or other organization, non-profit organization who are performing research. The validation data sets also must include a diverse population, and that's kind of maintained by the IRB board, who is actually trying to deal with the AI model being developed and deployed. And also like the model's result is being like evaluated on different kind of metrics, where we see that okay, if the data that was put in is kind of representing a larger population, not just a small scale available in that clinic. One, like the part that where I have worked mostly is with remote healthcare, because remote healthcare is something that's like envisioned to come upon in 5 or 10 years and kind of shift or revolutionize healthcare altogether. Remote healthcare stands for the wearable devices that we wear right now. It's just like you kind of can think of it about as an input of the like health status that you have currently right now through the wearable devices and also remote monitoring apps. The next part is actually working with the data and kind of building those AI models for predictive diagnosis. So the surge in remote healthcare happened like between 2000 and 2020, and it like burst up during the COVID, which is like pretty obvious. Beforehand, people were only thinking about AIs in terms of electronic health record data and kind of working on that predefined data. But after wearable health devices became popular and also telemedicine and telehealth came into play, AI basically showed like there are other possible scenarios where you can go into predictive diagnosis from the remote data that you are getting from the patients. And this has like, this is a profitable industry as well, which has seen a large growth again from the COVID era. And it's like most of the clinicians and doctors are really depending on the wearable devices right now, because there are two things that's good about the wearable devices or remote health monitoring. One is it lets them keep track of their patients when they are not around them, and the other thing is they are really cheap as well, which is like a big burden for patients when like in most cases where they don't really have the means to actually visit or have some directions about where their disease is going. So in those cases, remote monitoring is something that's like really have shed some light and shown pathways. So next part of our lecture would go upon something that shows that how these remote health monitoring works, because it seems pretty tough to actually talk about a patient's health with just the data from their wearable devices or their face video or their audio or something like that. So remote health monitoring is heavily depend on the physiological signals. So physiological signals are something that you can think about your body's way of telling how is it performing. We have like the most worked on physiological signals in terms of AI models. We have many, but most worked on are pulse rate, PPG signals, EEG, and also blood pressure. So what happens is most of the time there is no single physiological signal that is taken into account when you are building some kind of predictive model. It's kind of a combination or a multimodal model where it takes into input several like dimensions and tries to figure out how to actually work on predicting a certain kind of situation or stress related problem with these physiological signals. So one cool physiological signal is photoplethysmography or PPG, and remote PPG as well. So it came about in 1990s with the advent of pulse oximeters. Like beforehand PPG was invented, but it was not used widely, but pulse oximeters made it like really relevant. So the idea behind PPG is you have an emitter and a receptor. So the amount of light that passes through the skin and like gets reflected, it kind of it calculates the change of light absorbed and reflected and tries to predict the volume change, the blood volume change behind the skin, beneath the skin. That's touch based PPG. The remote PPG goes a bit further, where it tries to calculate the diffraction of light when it's shed upon the skin, and does the same thing, kind of tries to figure out the changes in blood volume. And the changes in blood volume is really related to how your blood is being pumped from your heart and other physiological signs as well. So the idea is, if you are like thinking about capturing PPG signal remotely from a face video or from a fingertip video, the idea is you first get a video of a duration like 10 seconds or 20 seconds. As videos are basically nothing but collection of frames, you kind of evaluate the pixels inside each and every frame. You average it out and you get the signal or the response for that second and for that frame. And if you plot that out over time, if you have 10 seconds or 20 seconds of video, if you have plot that over time, you kind of get the PPG signals for that duration, for that person or individual. Now if you have, let's say if you have got that PPG signal, the next part or the most important part that we have talked before feeding it into the model or before feeding it into some kind of prediction model, you really need to get the features of those signals that you have extracted, and these features come from specialized like researches that have been done before on this signal by like looking at what's a predominant way to actually capture or resemble certain kind of scenarios from that signal. Let's say you are working with a PPG signal, you can think about taking in the systolic peak, the diastolic notch and the diacritic notch and the diastolic peak. What it resembles is whenever your blood is pumped from your heart, it raises a systolic peak, then kind of the blood shrinks down and it like stables out. That's kind of what diacritic notch means. And the diastolic peak is kind of a second wave of blood pushing through your vein. And if you can combine these kinds of features and also do some mathematical evaluation on them, like first derivation and second derivation, you kind of also can emulate what the variance of different kind of PPG signals from different persons, and all of these features together inside an AI model can predict the predictive diagnosis modeling that we were talking about. So there are different machine learning models that have been used in this area. So the most frequently used ones are support vector regression, where we are looking for a certain kind of value for each and every feature set that we have like trained our model on, and these feature set can come from both time domain and frequency domain and can be also a combination of both of these. Support vector regression basically tries to pinpoint actual value. Let's say you are trying to figure out the oxygen saturation level of a person. So you kind of first train the model with the PPG signals and the associated oxygen saturation. Support vector regression is a model that can be really good in high dimensional data and kind of predicting the actual oxygen saturation by kind of finding similarity between different kind of PPG signals that it had been fed in, and also tries to output by seeing similar kind of PPG signals whenever it is actually in the work. Other kind of AI models that are seeing some light as well are transformer models, which are heavily used in generative pre-trained model like ChatGPT, natural language processing that we have already seen. Neural networks are heavily used for image segmentation and drawing on data from image analysis in healthcare. And one other model that's like often used but not really talked about is active learning cycle, where what happens is you train a model, it tries to predict some kind of solution that you are expecting. Whatever it does, you kind of feed it with the value that if it has done something good or something bad, and it takes into account that as well. So you can start with a very limited amount of data and work up from that. And active learning cycle basically gets better and better over time when it sees a larger population of data being fed into. So the idea after experiencing all of this was for me to make a automated health monitoring system from facial video. So the idea was I want to take face video of a person, then I want to extract features, relevant features, feed it into a model and kind of get the output, desired vital sign output that I want. In my case, it was oxygen saturation and respiration rate. One other thing that remote monitoring is really like good, or there is a possibility, huge possibility of remote monitoring, is the actual prediction or forecasting of vital signs. So if you think about it, when you actually have the predicted or the actual PPG signal or oxygen saturation value over time, and if you are seeing that over a longer period of time, as remote monitoring is something that you can wear and go around for days, even months, you can, with that data, you can actually predict what's going to happen for the future as well. So that's something that vital sign forecasting is being worked upon heavily. So but the data of these wearable devices can be used to actually predict if the person is going to have some kind of physical ailment in the future. Predictive diagnosis also works on calculating complication risks, which is really important for insurance companies whenever they are dealing with a person with huge health risks. It also lets the clinical diagnosis knows that if a person who is coming in with certain kind of risks or certain kind of certain level of risk, what is the chances of they being readmitted with the same kind of diagnosis. And prognosis and diagnosis is something that we have already talked about. One other thing that is often used when we talk about physiological signals and AI in healthcare, people are trying to actually convert the AI, if you have a PPG signal of a person, they are trying to construct the ECG signal from the PPG signal by modeling signal to signal transformations. And also there is an important missing part when you are working with physiological signals, that is they might be noisy, and to reconstruct those noisy signals, these kind of transformation models like transformer architectures and neural networks are being heavily used. I am currently working on something like this. I am trying to mimic PPG signals collected with non-infrared light to infrared light by collecting data from both the cases. And there is kind of a futuristic plan for healthcare with augmented reality and virtual reality as well, where all of the data or all of the ideas that I talked about, where the patient was remote, even the doctors are being thought of being remote as well, where wearing a virtual reality or augmented reality gear and performing all the diagnoses from the patient is outside the hospital, doctor is outside the hospital as well, and all the data that's being fed into them remotely is gonna help them in predicting the remote diagnosis from whatever they are doing. And this idea of actually making a medical facility not really prominent when you are dealing with just a diagnosis is catching up fire as well in different kind of scenario. But this is a bit far-fetched right now, but not impossible with the technologies that we have. The next few slides, or where I'm going to end my presentation, is with the ethical challenges that we face and like don't often talk about when we talk about AI in healthcare. The most prominent three things that I think are accuracy and fairness for the models, then how will the clinicians be supportive of the model that the developer has developed, and also how will they impact the job of the clinicians as well when the AI models are actually being used. So these three parts are something that usually face most of the questions when you are talking about ethical challenges in AI. And in most cases, the most like the most idea that's being shared on the topic is on human replacement and dehumanization, that with the advent of these AI models, do we even need the clinicians? My idea is this is a 50-50 kind of thing. You can't really remove the clinicians. Up until now, it's not at that stage that you can only depend on a model's prediction. To actually regulate these kinds of models for these ethical challenges, FDA has already implemented an algorithm for all the life sciences AI algorithms that's going to be used in real life scenarios. So the idea is not only evaluating the model during the generation, but also evaluating the model each time it's predicting, and kind of go over this on iteration until you are absolutely sure that the model is performing perfectly over and over again. And this has been enforced by FDA in all of the AI models that in any kind of life sciences or healthcare technologies that people want to use. One important thing about data when you are working, because AI models are really dependent on data, is the biasness and fairness of data that you are putting into the AI model. So there are two kinds of bias when you talk about biases in computer science. One is the data bias, and the other thing is the algorithmic bias. So the data bias comes from the data itself. If the data itself doesn't represent a larger group of population, a diverse group of population, it will have an inherent bias. One other kind of bias that we often not talk about is algorithmic bias. The algorithms are basically defined by humans as well. So if you don't represent, the ones who are building the algorithm don't represent a larger group or diverse group of population, it's inherently have to have some kind of bias. To deal with that, there are two schools of thought. One is to actually separate the idea of data and idea of model itself from the development or design stage. So whenever you are dealing with a certain kind of data, the first thing that you need to make sure is if the problem that you are trying to solve is kind of a representation of a larger group of population. For the algorithmic fairness, it's not pretty easy to solve, but the idea, there are some mechanism where you can build an algorithm based on certain ideas that are that make sure that at each stage where the algorithm is making some sort of prediction or some sort of calculations, it doesn't fall into different kinds of biases, and you do that over and over time and kind of keep a scoring of the algorithm that you are using, that the data that it's producing or the data that it's predicting is not falling short on the biasness that we think about. Ensuring data privacy and security is another part where AI models need to pull up, because the data that they are dealing with is really sensitive and they can't really spill down on. So ensuring data privacy and security is something that's another part where AI in healthcare is being heavily researched on. So before we end, the idea is AI in healthcare is already present and it's already making impact in several fields. It's up to us right now if we want to accept it or we want to like keep it away or think about it in a way that it's not really usable where a human can make certain decision. My idea is AI is a very efficient and very powerful tool when you are making certain sort of decisions. So the idea would be AI would make enhanced patient's care. Accurate information would be available for the patient, like their vital signs, whatever they want to know. Even the doctor's decision wouldn't be a black box for them. Obviously reduced care cost, because that's why like that was the motivation of most of the research, that building or using AI models for healthcare solution would take down the cost. Drug discovery is another thing that we want to like introduce drugs which are health efficient or health concerned, and data analysis and improved diagnosis is something that AI models are trying to like bring in, which wasn't really possible. You couldn't really think about how the data, medical data was validated beforehand, but right now with the advent of AI models, you can think about the diagnosis as well, where it came from and what's the validity of it. And with that, I would like to end my presentation, and if anyone from the audience have any questions on the topics that I shared. Okay. Sure.
So I'm curious about the bias in artificial intelligence with respect to the healthcare.
Mm-hmm.
It seems to me that you're trying to train the model
Mm-hmm.
to reduce bias,
Mm-hmm.
which requires a human input.
Mm-hmm.
But is there any guarantee that human bias doesn't influence the AI bias as well?
Mm-hmm. Like that's kind of a conundrum that's being faced in most of the AI implementations right now. So the data that you are working with, how about that? I mean, if that's inherently biased because that's being generated by humans in the first place, right? That's what your question is, as far as I understand. The thing is that about that, most of the work right now where AI models are being used actually worked on a pre-processed data, not the actual data that's being fed into. And when we actually work with these kinds of data, what we first do is kind of do some statistical analysis and see what kind of variation and variance and what kind of biases that we have in the data. If you have those kinds of biases, there are some ways which are called class balancing, so that you can balance certain data or variance in data before even feeding it into the model. These are some like ideas which was introduced when AI models were being like invented. But other than that, if the data is inherently biased, the idea is to like either work with someone who can like direct you to some idea that will let it enable the variance or remove the like bring in the diversity that you want for that such for the use case that you're thinking about. Other than that, like if the data is biased, the AI model will have the prediction that's going to be biased in some sort of way. So it's on the developer or the researcher that's working on the model to ensure data that's not biased in the first place. Mhm.
So I have a pair of questions and then a separate category question. So you mentioned active cycle learning.
Mhm.
Were you referencing gradient descent there and reinforcement learning?
Mhm.
I was just curious because I hadn't
Oh,
heard.
this is the first part of your question.
Yes.
Okay. So active learning is a bit different from gradient descent or what was the other one? Reinforcement learning, sorry. So reinforcement learning and gradient descent is basically a optimization problem. So gradient descent is used when you actually have the model, it's already like predicting some values, and you kind of like minimize the loss function that it has with gradient descent with some kind of optimization theory. So with active learning it's a bit different. You are not trying to minimize the loss, you are just trying to see how, like, it's kind of minimizing the loss, but you have already built the model, you are actually predicting outputs, but you are seeing that how far is it from the actual value itself, and that actual value is actually available by the user who is using it. So in the active learning process, you actually need a huge group of people who can actually validate the output that you are giving it. That's what the idea of. So this is something like, have you used Amazon Turks, where you can post a job? Like a job can be something like, if this is an image of cycle, click, tick yes or no. Right. So with active learning models, what people who build active learning models, what they do is, after building the model, they set it up on these similar kind of platforms where you can assign people some tasks, where their task is actually to validate the predictions of the model.
Oh, so similar to the training Amazon was doing on the unverify your human images, and
Yeah.
OpenAI I think was doing human-supported reinforcement.
Exactly, yeah.
Okay.
And reinforcement learning, then we will come into reinforcement learning. Reinforcement learning is, this is a pretty interesting topic of AI, even with all of this. Like, if you know that the inventors of reinforcement learning recently received the Turing Award for 2024, they received it in 2025. The idea behind reinforcement learning basically stems from the actual idea that Alan Turing had, where AI was thought of kind of like a seminal intelligence, where it will learn by experiencing, not learn by training data or trained data. So reinforcement learning is something different altogether. It's a different kind of concept from neural networks or regressions or classifications model. Reinforcement learning, what it does is it kind of it specifies an agent which can interact with the environment, and the idea is similar to active learning. So you kind of get input from the environment, see if the next step that you are taking is kind of maximizing your reward. Reward in this case can be if I can reach to you by reaching the steps. So at each step, if I'm a robot, I'm going to calculate how far my distance from you would be.
Okay, so it's a GAN, right?
It's not a GAN. GAN is a like totally different thing with different idea. Reinforcement learning is, GAN doesn't start with something like, you can start reinforcement learning without even any data passed on. So you just say that you want to reach, what's your name again?
David Sanchez.
And so you want to reach David. So my idea, at each step, I just want to calculate how far I am from David. I don't need any data. By like taking many steps, I'm going to figure out how I can like get to David efficiently, if I'm going in the right direction, if the distance from me is David is actually increasing or decreasing. And at each step also, if I am falling down, if I'm going on the other direction, something like this. GANs are a total different scenario. GANs are something that's like trying to generate a data based on like the input that you have given it, and GANs have two parts, a generator and a discriminator, and the discriminator kind of tries to like decide that the data that you have generated, is it good or is it bad, is it close to reality or is it fake, and doing that multiple times kind of gets you. And GANs involve the loss optimization problems, or like the optimization, the gradient descent optimization problem that you're talking about.
The second category of question I had stems from me having presented on the topic at a state higher education conference. How do you believe the AI work being conducted in healthcare, especially your signal-to-signal transformations, could be applied to predict at-risk students for positive intervention?
So in terms of like, if I think about kind of, this would be kind of a risk assessment for the students, right? With the data that I have on the students. For that, the idea would be to actually, so what am I trying to predict, if you could specify?
At-risk students are those that are typically considered not likely to succeed to graduation.
Okay.
That is kind of the success mark.
And the data that I have on the students would be their grade?
Yeah, GPA,
Probably.
the traditional stuff that any professional would look at and go, we may want to get them to tutoring, we may want to have some other type of structural intervention here, various other resources.
So for this, this would be a classification problem. So where I want to classify each student or label each student if they have, like they show a certain amount of risk or not, and if they are associated with certain amount of risk, I want to label them as someone who might not graduate. To do that, the idea would be to actually get the demographic information of the student, because my understanding is it plays a crucial role. Then the one other important aspect of these kind of problem would be the actual student record, if it's possible from their school as well, from their college as well, because people who actually are motivated to actually like become successful show it from a really early age, so you'll see that as well. And one other important key point that might be crucial or relevant would be their progress report throughout. Not only the GPA that I'm thinking about, I'm just like, we want to look into his or her history, and not just like when he started the journey in some kind of university or state level school, because without that history it would be a bit difficult to actually narrow it down. And obviously the reports that I'm talking about would have some kind of like evaluation, that is the student doing good or bad, that would give the model a direction to actually predict if the student is doing good or bad. If you can build a data set like this and kind of start evaluating the percentage or the like the probability of a student being like not doing good in high school or like the university, I think it would be something that you could start your work on, and that would also, like, it might not at first give you the actual result, but it will at least send you to the right direction, and with some iterations it should be good. One other thing that we have for Adams State right now, I don't know how much further that we go before, Blackboard is a really good source of data that I had seen. So you have their coursework, you have each and every scores of their assignments and quizzes. This is a very rich data source. So if you have something like this for 5 years or 6 years of data, that's really good for these kinds of models.
With that being a rich data source, do you think there's enough data within Blackboard and the other database systems within the institution to create such a model just based on fall semester to end of fall semester?
I truly believe so, that's possible. Blackboard is doing that. Blackboard is actually, in Blackboard Ultra, we have analytics for students. Where is that coming from? That's basically coming from the data that's already fed in Blackboard. If that's possible, this is obviously possible.
Okay.
Yeah.
Thank you, sir.
Yeah, thank you. Okay, I think then that would be all. Thank you all again for your presence.